Hello! In this video I'm going to be going over a specific heat problem that's a little more difficult than some of the other kinds. It deals with the law of conservation of energy, which states that energy cannot be created nor destroyed. So this means that energy lost by one system has to be gained by another. It's represented by heat loss equals heat gained, or Q equals Q. And so Q is the specific heat equation, so that could also be written as C times M times delta T equals C times M times delta T. Delta T being change in temperature, M being the mass, and C being the specific heat. And usually this is done where you have a metal or some sort of substance that is warm and it's giving off heat into to a cup of water, is what we did in our experiment. Alright, so we have a scenario like question 11 right here. It says a piece of unknown metal with a mass of 5.19 grams is heated to 100 degrees Celsius and dropped into 10 mils of water at 22 degrees Celsius. The final temperature of the system is 23.83 degrees Celsius. What is the specific heat capacity of the metal? So that's C. Attempt to identify the metal using the attached data. Alright. So, we've got a piece of unknown metal with a mass of 5.19. Let's say this side is my metal side, this side is my water side. So, 5.19 grams, that's my mass. It's heated to 100 degrees Celsius. Alright, so that's going to fall under my change in temperature. Got 100 degrees Celsius. It's the final temperature because it's heated to, so that's the final temperature of the metal, and dropped into 10 mils of water at 22 degrees Celsius. The final temperature of the system is 23.83. So after it cools down, it's going to be 23.83 degrees Celsius. Does it give us our heat capacity of this metal? No, it doesn't, so that's our C. That's what we're looking for. Alright, then we got specific heat of water. That's always 4.184 joules per gram degree Celsius. And then we got the mass of water, 10 mils. Alright, so when we're talking about water, 1 mil of water is equivalent to 1 gram of water. So we basically have 10.0 grams of water, and our change in temperature, so our final temperature is 23.83, and I didn't leave enough room, minus our initial temperature, 22 degrees Celsius. Final minus initial. Alright, now the tricky thing is 23.83, that's the final temperature of my system. But we have final minus initial. Here we have initial minus final. Why is that? The reason we have that is because we have to represent the energy going away from one system and into another. So that's why our final minus initial needs to be flipped for one of them. And that would also work if we flipped this one and had this be the regular final minus initial. But the reason we're showing this is because we're showing the energy starting with the metal and it's going into the water. So that's that reason. So the next part is a calculation that requires a calculator. So you're going to have to get your calculator out. Fortunately, I always come prepared, so I have my calculator right here. And I'm glad you came prepared too. Alright. So we've got 4.184 times 10. Oh man. Alright, 23.83. Let's figure that one out. I've got a old school calculator that isn't as nice as those graphing ones. I'm going to put 1.83. Alright. Times it by 10 times it by 4.184. Alright, that gives me, ooh, my screen went black, gives me 76 point, I'm just going to round it to 57. And we got C, alright, 100 minus 23.83. 76.17 times 5.19, 395. Alright, divide both sides by 395.32. $76.57 divided by 395.32 gives me 0.19, and I'm going to round it to 3 sig figs because that's the least amount of sig figs in my problem. 94. So going back to my original problem, 3 sig figs, 5 sig figs, 4 sig figs, 3. Least amount of sig figs is 3. Alright, and we're talking about my C, which is specific heat. Specific heat is always joules per gram degree Celsius. And that's the specific heat of my metal. That's how I do a more difficult specific heat problem.